pendidikan dan non-kependidikan. Berkomitmen untuk mencetak insan-insan unggul, menyiapkan lulusan yang tangguh, serta siap menghadapi kemajuan dunia. Fakultas Matematika dan Ilmu Pengetahuan Alam UNESA memiliki komitmen dalam menyelenggarakan pendidikan berbasis ICT melalui metode pembelajaran inovatif dan berbasis riset sesuai dengan perkembangan zaman.
Bertepatan dengan berdirinya IKIP Surabaya tahun 1964, lahir pula Fakultas Keguruan Ilmu Eksakta yang menjadi cikal bakal dari Fakultas Matematika dan Ilmu Pengetahuan Alam. Kemudian setelah diresmikan menjadi Universitas Negeri Surabaya dengan tetap menjalankan visi utama sebagai lembaga penyelenggara program pendidikan dan non-pendidikan, maka kini FMIPA UNESA memiliki 5 jurusan dengan 9 program studi. Tak hanya berfokus pada pendalaman materi kemipaan, namun setiap sivitas akademika juga dibekali dengan soft skill seperti MIPApreneurship, kejujuran, kedisiplinan, kreativitas, berpikir kritis, kolaborasi, komunikasi, manajemen, inovasi yang solutif untuk memecahkan problem dalam kehidupan bermasyarakat dan berbangsa, juga kemampuan mengintegrasikan pendidikan dan ilmu MIPA dengan kapabilitas entrepreneurship atau yang kami sebut dengan kompetensi ekopreneurship. Pelaksanaan tridharma, penentuan target, dan pengembangan di berbagai bidang menjadi capaian wajib bagi FMIPA UNESA. Komitmen ini diwujudkan dengan didirikannya dan difasilitasinya gugus penjaminan mutu FMIPA UNESA dalam menjalankan tugas dan fungsinya.
Penyelenggaraan administrasi dan tata kelola FMIPA UNESA dirancang untuk selalu akuntabel, transparan, adil, dan otonom. Sistem administratif yang baik juga bertujuan untuk menjamin mutu sekaligus berkomitmen dalam peningkatan kualitas setiap sivitas FMIPA UNESA. Demi terciptanya lingkungan pendidikan yang asri, Fakultas Matematika dan Ilmu Pengetahuan Alam UNESA mengimplementasikan program-program ekokampus. Di antaranya dengan menyediakan ruang publik yang bersih dan teduh, juga melaksanakan beberapa program lanjutan dengan menerapkan sistem pengolahan sampah metode 3R, reduce, reuse, recycle. Sekaligus menciptakan berbagai produk untuk memelihara dan menjaga keanekaragaman hayati. Matematika dan Ilmu Pengetahuan Alam UNESA mewujudkannya melalui kerjasama dengan berbagai instansi, baik tingkat regional, nasional, hingga internasional. Berbagai sarana dan prasarana yang lengkap menjadi salah satu upaya Fakultas Matematika dan Ilmu Pengetahuan Alam UNESA. Upaya tersebut menjadi bentuk keseriusan UNESA dalam menciptakan ekosistem yang produktif bagi mahasiswa, menunjang kegiatan penalaran, hingga mewujudkan berbagai inovasi terbaru. Kreatif, inovatif, serta berprestasi dalam bidang akademik maupun non-akademik, baik di tingkat nasional hingga internasional. Dalam upaya memperbarui dan mengembangkan eksplorasi pembelajaran, FMIPA UNESA secara konsisten menghasilkan sejumlah riset hingga publikasi pada berbagai jurnal terakreditasi. Melalui program pembelajaran terapan yang diaplikasikan berupa pengabdian masyarakat, dihasilkan sejumlah inovasi yang menjadi solusi atas berbagai problematika lingkungan. Terus berinovasi, mewujudkan inspirasi menjadi sebuah prestasi, membentuk lulusan cerdas, berwawasan lingkungan dan berjiwa ecopreneurship bersama Fakultas Matematika dan Ilmu Pengetahuan Alam Universitas Negeri Surabaya.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Can you hear my voice already?
Ya, Bu. Ya.
Okay. Good morning, ladies and gentlemen. My name is Meta. It's a wonderful and precious chance for me to be your host in our big event, JPFA Editorial Workshop with the theme Global Trend in Physics Research. First of all, let's say thanks to Allah who has been giving us guidance, happiness, healthy, and mercy, so we can attend and participate in this event without any obstacles. In this beautiful day, I would like to say welcome to Associate Professor Dr. Hisamuddin Zainuddin, Professor Dr. Vida Rahmadiarti, MKes, and Dr. Binar Kurnia Prahani, MPD. Ladies and gentlemen, on this occasion, allow me to introduce to today's agenda. First, we are listening to Indonesia Raya and Mars UNESA. Second is the welcoming speech from the head of Scientific Publication Division, Universitas Negeri Surabaya, Dr. Binar Kurnia Prahani, MPD. And the third agenda is welcoming speech and opening from the Vice Dean of Academic Affairs, Faculty of Mathematics and Natural Sciences, Universitas Negeri Surabaya, Professor Dr. Vida Rahmadiarti, MKes. And then we have the photo session. And after that, we are step onto lecturer presentation by Associate Professor Dr. Hisamuddin Zainuddin from University Putra Malaysia. And the next agenda, we are going to have a discussion or question and answer session. And the rest is the closing. Okay, for the first agenda, we are going to listen to Indonesia Raya and Mars UNESA. Okay, step on to our next agenda is the welcoming speech from the Head of Scientific Publication Division, Universitas Negeri Surabaya, Dr. Binar Kurnia Prahani, MPD. To Dr. Binar, time is yours.
Okay, thank you, Miss Meta. Can you hear me?
Yes, we can hear you.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everybody. Yang terhormat Profesor Dr. Hisamuddin Zainuddin from University Putra Malaysia, pada Profesor Dr. Vida Rahmadiarti, Wakil Dekan FMIPA UNESA, Ketua Panitia, Pak Alan Utama Deta, selaku juga Managing Editor, dan tim JPFA yang telah meluangkan waktu, kami sampaikan terima kasih banyak, dan para peserta workshop yang telah meluangkan waktu juga, semoga menjadi kebaikan kita bersama. Terkhusus untuk mempersingkat kalam, kami sampaikan kepada Prof. Hisamuddin. Thank you very much, Prof, for your aware.
It's my pleasure.
Yes, thank you very much. It's hope that time and hope can contribute positively to improving the quality of our journal, especially JPFA, Jurnal Penelitian Pendidikan, Penelitian Fisika dan Aplikasinya. It's one reputable journal from UNESA, in second rank Sinta. Semoga yang akan datang, Prof. Hisamuddin dapat meluangkan waktu dan pengetahuannya, Prof, untuk meningkatkan kualitas di JPFA, yang mana besar harapannya di 2023 bisa terdaftar di Scopus ataupun Web of Science. Itu saja dari kami, harapan besar semoga Prof. Hisam dapat membantu dan menjadi editor ya Pak Alan. Ya semoga, dan bisa berkunjung ke UNESA pastinya Prof. In the next year, can visit Indonesia, especially Surabaya. We can eat rawon setan or bebek sinjai. It's our favorite food in this. Okay, I think it is enough. Thanks for your time and all for this workshop. Ihdinas siratal mustaqim. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you, Dr. Binar, for the speech. And now we are going to have a welcoming speech and opening from the Vice Dean of Academic Affairs, Faculty of Mathematics and Natural Sciences, Universitas Negeri Surabaya, Profesor Dr. Vida Rahmadiarti, M.Kes. To Profesor Vida, time is yours.
Terima kasih Bu Meta. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi dan salam sejahtera bagi kita semua. Yang saya hormati Associate Profesor Hisamuddin Zainuddin dari Universitas Putra Malaysia. Selamat datang Prof di UNESA. Yang saya hormati Dr. Binar Kurnia Prahani selaku Ketua Divisi Publikasi Ilmiah UNESA. Bapak Utama Alandeta, MSI, dan tim JPFA yang saya hormati. Alhamdulillahirrabbilalamin, hingga pagi ini kita diberi nikmat berupa sehat, sehingga bisa berada di ruang Zoom ini dalam rangka workshop yang diselenggarakan oleh JPFA. Perlu kami sampaikan Pak Hisamuddin bahwa JPFA seperti yang disampaikan Pak Binar tadi sudah terindeks Sinta 2 di Indonesia, dan sebenarnya juga sudah pernah mendaftar di Scopus, namun masih ada perbaikan-perbaikan. Nah, harapannya nanti dengan mungkin tips yang diberikan oleh Pak Hasanuddin nanti bisa menambah peningkatan kualitas di jurnal ini, sehingga nanti insya Allah di 2023 diperbaiki apa kekurangannya, sehingga ketika nanti mendaftar di Scopus itu insya Allah akan terindeks Scopus gitu harapannya. Dan kami berpesan kepada tim editor JPFA untuk menggali sebanyak-banyaknya informasi dari Prof. Hisamuddin dan tadi Pak Binar juga mudah-mudahan tahun depan bisa hadir gitu nggih Prof, nggih kalau diundang di UNESA khususnya di FMIPA gitu nggih, monggo nanti bisa sharing, karena kami punya 19 jurnal Prof di FMIPA ini yang terindeks Sinta mulai dari 2 sampai 4 gitu, dan harapannya nanti juga menyusul setelah nanti ini fisika terindeks Scopus. Saya kira itu, dan tadi Pak Dekan Maidin kirim salam untuk Prof. Hisam karena beliau ada kegiatan. Dengan seizin Allah Subhanahu wa Ta'ala dan atas izin Bapak Ibu semua, kegiatan workshop ini dengan mengucap Bismillahirrahmanirrahim bisa dimulai. Terima kasih. Mohon maaf kalau ada kekurangan. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Prof. Vida, for the speech. And now we are going to proceed to our next agenda, presentation by Associate Professor Dr. Hisamuddin Zainuddin from University Putra, Malaysia. Before we start, let me read his curriculum vitae. Associate Professor Dr. Hisamuddin Zainuddin from University Putra, Malaysia is an experienced physicist with research expertise in theoretical or mathematical physics. He received his PhD in University of Durham in 1980 and has been working as a physicist since then. He also writes scientific articles in many international journals such as Journal Solid State Science and Technology Letter, Journal of High Energy Physics, and Material Science Forum. Okay, to Professor Hisam, time is yours. You may begin the presentation.
Thank you. Let me try to share this. How do I share? Sorry about this. The interface is a bit different. Oh yeah, share screen. So are you able to see my screen? My PowerPoint?
Yes, clearly see.
So,
Yes, we can see your presentation.
okay, let me put this on slideshow. I think I better use the PDF version so that I know how to control it. Just give me a minute. Okay, so Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Professors, UNISA, and also Professor Bina, Professor Deta, and the Dean. So let me introduce myself. Is my screen visible to everyone?
Yes, we can see your presentation on the screen.
Okay, good. So let me introduce myself. I'm a theoretical physicist. I used to work in two different organizations, which is the Department of Physics in University Putra, Malaysia, and also the Institute for Mathematical Research, which is short form as INSPAM, Institute Pendidikan Matematik. So, so I'm about to retire actually. So I'm really thankful that you have actually invited me so that I can share some of the things that I know before I sort of retire formally, which is sometime soon. Okay. So today, what I'm going to talk about is essentially the idea of quantum science and the language behind it that most probably not many people know about it. Okay, so some of it is actually come from my PhD research and also from research that was done by my PhD students. So, so let me begin. So here's the outline. Actually, I have not enough time to prepare much more, but I hope this will suffice. I'll be happy to discuss other things as well beyond this presentation. So today, what I'm going to do is I have about 4 parts to my presentation. So first is to talk some history of quantum physics, and then what are the essential what you call language behind it, and then some future possibilities that can be used to investigate new ideas like things like in quantum computing and so on and so forth. So let me just proceed. So here's some introduction, some preamble first. So I believe, I hope this is not too basic to everyone, but I believe there are students here. So physics essentially are often classed into 2. So there are classical physics and also quantum physics. Classical physics often describe macroscopic objects, and for quantum physics, they often describe microscopic objects. But the distinction between the 2 is not necessarily by size. You can also have macroscopic quantum objects. Things such as superconductivity and superfluidity are essentially macroscopic objects. So, so how can we actually differentiate between the 2? One has to actually go into the formalism or the language behind these 2 different theories. Okay, so there are essentially in the normal quantum mechanics, one often divides a classical world, which is obeying classical physics, and then you have the quantum world, which is obeying things like Schrödinger equation and so on and so forth. And this cut essentially is called a Heisenberg cut, and it depends. It's not strict in some sense, because you can actually shift this Heisenberg cut to almost anywhere you want. So these are things that probably a bit more complicated and it's a bit more philosophical. So Heisenberg cut is also there when one uses the Copenhagen interpretation of quantum mechanics. So there are some good articles that probably I want to highlight is the article by Josh Ellis, which is telling you how you do some kind of coarse graining as you go to different levels of physical systems. So these are probably one of the best articles that I've seen so far describing this matter. So again, I'm still just giving you some ideas about the history. So quantum physics are always said to begin with Max Planck, which is in 1900s. Okay, but actually before that, there are even precursors of that. Say 160 years ago, quantum physics start in 1900, so they're about more than 100 years already. But even before that, we have things like Bunsen's spectroscopy, where you actually identify elements through heating certain materials. And then this was not really explained within the context of classical physics. And the other thing is Boltzmann's atomic hypothesis, which is, in a way, is a basis to what Planck's what you call formulation of the black body radiation. And before it goes to the modern formulation of quantum mechanics, there are a version of the theory, of quantum theory, called the old quantum theory. So these are normally understood in terms of Bohr's earlier works, okay, including with Sommerfeld, and then you have the quantization condition over there. And usually we think of in terms of angular momentum, but then you can generalize to the action quantity, okay, and then this has to be quantized, and there's no real explanation why that has to be so. And then the de Broglie matter wave hypothesis is something which is quite revolutionary in some sense, and there's no real explanation, but the most what we call unknown aspects of the de Broglie matter wave hypothesis is that it's related to theory of relativity, and so on and so forth. Okay, so and then we have after that we have the developments of the new mechanics called quantum mechanics, which is coming from the works of Heisenberg, Born, Jordan, and Schrödinger, and finally Dirac. And the language or the formalism of quantum mechanics sort of solidifies when von Neumann publishes this book. It was published in German language before that in 1932, but it has already been translated to English in 1955. This is Princeton University Press. Okay. So these are so I'm more into the formalism rather than the applications in this particular talk. I didn't have time to actually go into the rest, but we can discuss it if you want. Okay. Next, can you actually see my cursor, by the way?
Yes, bro.
Okay, good. So there are, we always hear that quantum physics is something that very few understand or nobody understand. And this sort of brings the idea of quantum mysteries to certain certain layperson or certain even physicists. Okay, but what are the problems in quantum theory is essentially there are a few different aspects. One of the aspects is essentially the uncertainty principle. Why it has to be that way, and this has been discussed quite a lot. And there are actually even variants of uncertainty principle, which I'm not able to say anything more than that because I have not done too much more on that. But there will be also some other signatures coming from classical physics, which I will tell probably towards the end. And then we have the Bond's probability interpretation itself, which says that your wave function, or more generally the quantum state vector, carries not definite information, but intrinsic probabilistic information. And this was essentially something that bothers Einstein quite a lot. So one of the famous quotes by Einstein is, "God does not play dice." So this is coming from the probability interpretation. Okay. And then also, I wanted to say more about this because, but I don't think I have time to do this. I wanted to say something about the EPR problem and the entanglement, but probably we can discuss in some way or another maybe later on. But me highlighting this thing is essentially because this year's Nobel Prize, the Nobel Prize work, the winning work of for 2022 Nobel Prize is essentially awarded to something which is related to entanglement. Okay, and entanglement is actually is a concept that has its origin in what we call Einstein-Podolsky-Rosen problem, which looks at the system of two particles, which is obeying some kind of conservation of momentum. Okay, in the more popular discussed version is not using the momenta per se, but it uses what we call spins, and this is essentially being discussed by David Bohm in his book Quantum Theory, which is published in 1951, and that becomes later on people discuss entanglement or the EPR problem through the idea of Bohm's version of spins. So these are the Nobel laureates for the 2022. You have Alan Aspect, John Clauser, and Anton Zeilinger. Let me just say what they have done. John Clauser is the pioneer in doing the experiments to check the correlation between two particles, but in this case, essentially photons, really, sort of violates certain relation called Bell's inequality, and says that a local classical version of it cannot be actually producing those kind of violation of inequality. And then the experiments, as most early experiments do, they have loopholes, and Alan Aspect sort of close some of the loopholes. And then Anton Zeilinger also did, so these are based on Bell's work. Anton Zeilinger did something else, which is on GSZ state, which also talks about particle being correlated, sort of tripartite kind of equation. Okay. So, and that sort of pioneered a new area called quantum information science. So these are quite important things that people are pursuing today. So probably we can have a short discussion on this as well. So, but all of this so-called violation or the strange thing, the mysterious things, actually comes from the language itself, the mathematical language itself. So I'm going to go into that. So what are the language being used inside quantum theory? So these are essentially the first pioneering years of quantum mechanics. So in order to build a language for quantum theory, normally what one does is to actually, okay, you model it classically first, and then we try to actually give a slightly different language to make it in a way like behaves like a quantum objects. So we talk about classical observables. What are classical observable in this particular case? They are simply functions, and functions of what? Functions on the phase space. So the phase space are normally considered by the position and the momenta of position and velocity. Okay. So these classical observables is what you find in classical mechanics, essentially. But now you need to be able to change those to what we call the quantum observables. And quantum observables are essentially operators acting on a Hilbert space. So what would be the right way to do things? What is the procedure to make it going from functions to operators? So what Dirac did was to actually observe there is a kind of algebraic correspondence between what they find in classical mechanics and what they find in quantum mechanics. So the one in classical mechanics, you have what we call the Poisson bracket algebra. So you have two functions put together, and then you form derivatives of those two functions, and then you take the antisymmetric combination of those. And that seems to point to a certain similarity with the commutative algebra of quantum observables. So normally these are given in terms of, say, the what is known as CCR, Q, XP equals to IH bar kind of thing. So you have that also in the classical mechanics as well in the quantum mechanics. But in the classical mechanics, they are just functions. In quantum mechanics, they are essentially operators. So, so there are a set of rules which I did not quite write it down over here, but there are things like linearity, some scalar multiplication. So those rules are not that important to us, but the one that is important to us is essentially the algebra. So we have the Poisson bracket of say X and P equals to the identity or equals to 1 correspond to the commutator Q and X and P equals to IH bar, the identity. Okay? And these can often be realized by these kind of operators. So you can write your X, which correspond to the position, as simply a multiplication operator. So it converts your wave function psi x to something which is multiplied by x. Whereas as momenta times psi x will be just the derivative. So these are going to be very important for us because there are different quantization procedures and you have to actually pick one which is suited to your liking in some sense. So we'll talk about that in a minute. Now, the Dirac rules, now it's quite funny in some sense. Dirac pointed this out. Let me go back to the previous page. Dirac pointed this out in 1925. Okay, but it was and assume that this is actually true for for any functions of the observables. Okay, but unfortunately, sometime in maybe I should go to the next slide. Sometime in 1946, and then followed by a work in 1951, they show that there is something wrong. Even with this derived rules, which was initially assumed that it works, but that cannot work for all kind of observables. So let us look at why is that so. Normally, when you talk about quantum mechanics, the standard example would be things like harmonic oscillator. So the harmonic oscillator will have things like P squared, okay, correspond to the kinetic energy, and then H squared correspond to the potential. So, and essentially there's no problem there. Quantum, the direct rules are sufficient essentially to do the quantization, converting of the functions into operators. But now let's consider beyond quadratic. So here is just writing the quadratic level first. So you have say X squared being written as Q squared. So the capital Q here is what we call the quantization map. And then you have QP squared. Okay, that will be now P simply is represented by a first order derivative. This will now become a second order derivative. But now you have to consider other kind of possibilities like multiplication of X and P. Over here, then you probably need to sort of find what actually works. And this is one operator that works. Okay? And then you can check with this, provided that we keep everything to the quadratic level. So there's no more than nothing bigger than X squared, P squared, or X and P. Then you find that the quantization map will always map the Poisson bracket algebra to the commutator algebra. Okay, that works fine. So let's move on to the next level. Then we go to the ternary level. So now you consider instead of quadratic, X squared, Q squared, XP, you might want to do something like X cubed, P cubed, XP squared, PX squared. And for the H cube and P cube, there's no real problem. You can use the normal way people do, but we try to find what would be the operator version for XP squared. And a thing that works is this particular second order derivative with first order derivative there, and PX squared would be first order derivative with an X over there. So it's a mixture of both X and the derivative. Okay? So let's try to see what is wrong with this thing. By the way, at this point, the assignment is fine. The assignment of the operators are fine. And you can even check whether they are Hermitian or not. Okay? Hermitian is a property that one needs for the quantum observables. And you can check that all these operators over here are Hermitian. Okay? So at this level, ternary combinations are fine. But then you have to remember that we need to do the Lie algebra correspondence. So in the Lie algebra, you consider the case of the Poisson bracket algebra, which is the classical version of it. So you have an identity. You have this combination of X cube and P cube as a Poisson bracket multiplied by this constant. You will always get X squared, P squared, and then another combination that gives you the same answer, X squared, P squared, okay, will be this Poisson bracket. So this is classical. So if the correspondence between the Poisson bracket algebra and the commutator algebra should correspond, then you should try to have a similar kind of thing. Okay, so here we do the quantum case. So you put a map of the H cube, put a map on a P cube, and see what they are, and then do the commutator, you get this particular answer. And we do the other one, the other part, which is looking at H squared and P squared X. For example, I think I miss out the B here, but never mind. It's coming from there, okay? And you'll find that, okay, you almost get the same answer, but there is a term over here that looks different. Here is a matter of a 2/3 H bar squared times the identity. Here you get minus 1/3 H bar squared identity. So in other words, even though the quantization map works for the ternary level, when you check with the hermiticity of the operators, it fails to comply the algebraic correspondence. So this is actually was known, as I said, very much later. You remember 1925, it was only discovered in 1946. Okay, that's the earliest. Okay, and then was subsequent, sort of slightly more general, was 1951. Okay, and this failure should make one be suspicious in a way, because you have to remember when we work with problems in quantum mechanics, you have terms appearing more than quadratic terms. Okay. So these are things that one thinks that all this ordinary assignment can work, but really one has to check. Okay. So these are things that probably is not really known to most people, I think. So so how do we settle this? And let me just also say the Gromov-Van Hove theorem, the original one, was applying it to coordinates of a linear space or a vector space, and your P is also a linear space. Okay, for nonlinear spaces, it's even worse. They have shown it for the case of the two-sphere, and even at the linear level, it's fine, but even at the quadratic level, it's already there's some problematic algebraic correspondence. So this is actually being discussed by these three guys. Grundling is actually my senior in University of Adelaide when I did my undergraduate degree. So they are actually discussing this kind of problems. Okay. So now, given that you have these problems, and how do one make sure that the mathematics that you use for quantum theory is actually workable? Okay, so they start to think of generalizing things that they know of what they know from the linear spaces where X and P belongs to a linear space. They look for certain things which is probably a bit more general, which is nonlinear spaces. Okay, so here we start to look at the different quantization programs. Okay. So here is the first what I call the first crossroad, and the first crossroad is to really understand whether we want to use quantum mechanics in the sense of build up from Hilbert spaces or not. Okay, so the resolution of this problem is really what? So remember the problematic case is the Lie algebraic correspondence. Okay, so if you take the Lie algebraic correspondence has to be true, then one has to limit the set of observables that one quantize. So one cannot just have every observable. You have to limit your set of observables. And how do you find that set of observables? We will talk slightly later. And then the other one to say is, okay, the Lie algebraic correspondence is only approximately true. So what one can do, you have your H bar, for example, is a small parameter. So you can say that, okay, it's true at least if you go to the powers of H bar squared. But you go to H bar cube, then you might have slightly different kind of algebraic correspondence. Okay, but if you limit yourself to approximately true, that means you'd say up to H bar squared, then you can say that all observables can be quantized, because you sort of ignore higher powers of H bar cube and so on. Okay, so having these two set of resolution of the Gromwell-Van Hoek problem, there are two different main directions of quantization. Okay, the first option is coming from what we call the geometric quantization. Okay, I will be I'm not an expert in geometric quantization itself, but I have what you call some experience with the other one, which is what we call the canonical group quantization. They both use what we call symplectic geometry, which I will try to describe in a minute. And then once your symplectic geometry sort of set up the classical version, okay? Remember the classical version is supposed to be just function on some space. Okay, so the space that we are looking at will have this kind of geometry, the symplectic geometry. And then we use those tools of symplectic geometry, and then later on I'll mention a bit what's being used. And then from there, one construct the Hilbert space. Okay, so that's one option. The second option is to look at this as probably more popular among mathematicians rather than physicists. Okay? Deformation quantization. So the idea over there is to look at, remember your Lie algebra or the Poisson bracket algebra, for example. What does one do? You take f and g as the functions, and then you sort of multiply these two functions, and then you take the reverse order, and then take the difference between the two. Okay, something like that. Okay, I mean with the derivatives and so on. But instead of just a product, the normal product that you know, it uses a different kind of product called the deformed product, and essentially this will actually helps you making it realizing in some way the Lie algebraic structure of the quantum sense. Okay, but again over there, depending on who you discuss with, the deformation quantization, you can produce Hilbert spaces. Okay, you can produce, but yes, it becomes an extra step. Okay, you deform the product structure, and then you look at the mathematical structure behind that, and then okay, if I want to start connecting this with the normal quantum mechanics, then I can actually build from that algebraic structure that comes from the product structure, the deformed one, and then build Hilbert spaces. So it's an extra step to actually make the deformation quantization to give you the Hilbert space. Okay, but as it is, with just the deformed product structure, what you have is just like a normal multiplication. Okay, but the multiplication is something different. I think I have it on the next page. Okay. So what they do is they introduce the idea of a star product. Okay. So over there, instead of just multiplying your functions over here, f and g, you have something else sort of deforms this product to give you a new product, which is denoted by this star here. Okay, and this extra thing is actually coming from some bilinear functions. This is actually B and subscript here. Sorry about that. So this is a bilinear form. So it takes the two functions, and then there is a differential operator acting on it, and that would actually give you what seems to appear like a quantum property. Okay, so in the end, what's relevant from there is that you can now think of this like your commutator. Okay, this part will look like commutator, and it corresponds to the Poisson bracket. But then it doesn't quite fit exactly because you have higher order terms. And these higher order terms are normally discarded. Okay, so this sort of form a different kind of school, which is the deformation quantization school. And it's quite popular because there is another kind of version of quantum mechanics, which is based on Moyer bracket. Okay, and they essentially comes from a particular operator. Well, actually, the operator ordering that one has over here is just a normal. If we take F and G, what does one do is to take the average of the two. So you have FG plus GF kind of thing, divided by 2. And that will be the Bond-Jordan operator ordering. Okay, and that gives you the idea of a Moyer bracket. Now, since this is actually being set up by a mathematician, one of the questions that they will ask is, okay, when you have a Poisson bracket on a particular space, these are called Poisson manifold or Poisson space. Okay. Now the question is whether you can actually quantize every Poisson space. Well, there is a general work by a mathematician. I'm not sure whether anyone knows this guy. He's a free medalist, Maxim Kontsevich. He actually proved it. No, if you have Poisson bracket structure there, then no, you can actually quantize. So that's why, to some school, this will be something which is more preferred. Okay. Let me go to the other one. If you have any questions, you can interrupt me if you want to, because this is a bit complicated because I didn't have time to do much more better version of this. The other one is I did mention this now, was the geometric quantization. Okay, and it assumes a particular space called a symplectic manifold. And this symplectic manifold is just ordinary space, okay, but it has one particular quantity called a symplectic form. Now, what is a symplectic form? If you do not know what it is, it doesn't matter, but if you know tensors, this is just an antisymmetric tensor. Okay? And this antisymmetric tensor has to be available at all of the points on the manifold itself. So, and with this structure, you can build what you call the quantization map, the big Qs over here, and then you can set up this property, the algebraic correspondence. But over here, you need to select the set of observers. At the moment, we don't have a principle of how to do this, okay, for this geometric quantization. So one of the things about this symplectic manifold that most of the time that one has is we have what we call a cotangent bundle structure. Okay, you can think of a space and then you draw tangent vectors on the points on the space. So that would be a tangent bundle. Okay? The collection of points of the space together with the tangent vectors. Okay? So these are things like, for example, your position and velocities. Velocities will be tangent vectors. Now, normally we do it using the what you call the momentum vectors. So we normally take the Hamiltonian, for example. The Hamiltonian uses momenta instead of velocity. Okay? So the momenta lives on a different bundle called the cotangent bundle. So never mind what it is, but it's just an extra structure for that. Okay? Now the cotangent bundle usually are what we call, they are not compact. So you can think of it as it goes on, say, infinite in one direction and infinite in another direction. So it's not compact. I'm not sure whether, I don't know how to say it. If you think of a sphere, for example, a sphere is compact because it always goes back to the same amount of space. Okay, and usually what happens in this is related to our work, we would like to consider, for example, qubits. And you know, qubits are defined by the Bloch sphere. Okay. So, and the Bloch sphere is a compact thing. Okay. So one of the current work that my PhD student is doing is essentially to extend from a cotangent bundle structure, which is actually, it's not compact, to something which is compact. So this is the thing that we attempt to do. We are not really successful yet, but we are doing it. So what's involved with this geometric quantization is a bit involved. How much time do I have? Because these are details. So if you want to go to details, then I can go to details.
You still have much time.
Okay. So what one does in this particular case, okay, there is the idea of like the tangent vectors. Okay, the tangent vectors normally are obtained by taking the derivatives, right? But for cotangent bundles, we do what we call the differentials. So the differentials is something like your dxi over here. This is a differential of the coordinates, and this would be the differential of your momenta. Okay, and you take a product in this way, which this is called a wedge product. This gives you what we call an antisymmetric tensor. Okay, so this is the basis of one differential form to another differential form over here on different spaces. Okay, and then you take the product of those two, and then that product is antisymmetric. And this is essentially what we call the symplectic structure or symplectic form. And you can, if we have done a slightly modern version of classical mechanics, then one could actually look at the symplectic form. Okay, I'm jumping a little bit over here. The symplectic form acts on what we call the tangent vectors, okay, and that should produce the Poisson bracket structure. So what are the what we call tangent vectors over here? So here you relate this to some function. This is sometimes called, the function actually traces out a curve, and that function is called an integral curve. So this is a tangent vector in the phase space. Okay, so you have a derivative with respect to Q, you have a derivative with respect to P. So these are just like basis vectors over here. And then you have the rate of change of F with respect to P, rate of change of F with respect to Q. So they give you the idea of like tangent vectors on the phase space on the two different coordinates. Okay, so you take this as a tangent vector, and then you apply this to the symplectic form. Okay, and that is the way of doing this thing. I'm not showing you all the things, but you'll get back to the Poisson bracket structure that you actually see in ordinary quantum mechanics, also ordinary classical mechanics, without this geometric notion. Okay, here we are using geometry to do it. Okay, because you talk about tangent vectors, you talk about differential forms. And what one does is one can actually show this is like an operator already. If you look at it, no, this is a differential operator. So you can treat this like an operator. Okay, and then take the commutator. So you take the commutator of one tangent vector that corresponds to F, and also another tangent vector that corresponds to G. You get another tangent vector correspond to the Poisson bracket of F and G. And you can see that, okay, this seems to give you what we need, the Lie algebraic correspondence. Okay? But it's not quite enough, unfortunately. Okay, this is what we call, okay, here is the identification over here. You can use this, because you have this correspondence, you can use this so-called pre-quantization map to define a quantized version, a pre-quantized version of a function. So remember, you want to make it as an operator. So here's an operator. Here's the tangent vector above, which is an operator, and then this is something else, and then you do this to actually, because there are also nonlinearities that you need to figure out. Okay? So this is what we call pre-quantization, but pre-quantization is not the thing that we want for quantum. Remember, in the Schrödinger representation case, okay, we always have the operators depending only on X. For example, the position representation. For example, the X operator is just a multiplication operator of X, while the P operator is essentially a derivative with respect to X. So here, your operator is only acting on half of the phase space, which is just X. It doesn't have P there. So that's the picture of the Schrödinger position representation. Okay? So we need to cut down half of the phase space into two in order to be able to implement the Schrödinger representation. So that's essentially what we need. So there you need to introduce, this is a bit, it's a bit beyond me because there are details that I have to, probably too short a time to do. But here you can talk about, you have a space and then how you foliate the space in some sense, and then trying to find the right foliation, and that gives you a distribution. So this is what we call the distribution D on the phase space, such that, again, without going to details, you take the covariant derivative. If you have done relativity, you know that you need to do covariant derivatives. Okay, you have to compensate because your space is curved. Then you have to compensate how you compare two different vectors, for example. Okay, so you have to use the covariant derivative for a particular function phi, and if you restrict your phi within this distribution, then you should have equals 0. So essentially, just like implementing your Schrödinger representation, because your Schrödinger representation would be something that depends only on X. So it takes the covariant derivative with respect to P, because there's no dependence of P in your wave function, and it will be 0. So that was the idea. So let's keep. So in other words, once you have a polarization, then you can sort of define the better version of the quantization method. Previously, is you remember there's another term inside here, but now you get rid of that. Okay. So I use a different kind of quantization technique called the canonical group quantization. Now the idea here is almost the same like the geometric quantization, but what happens over there is you really focus on the symplectic structure. Okay, so the idea of Chris Isham is a if you look through his papers, he works on quantum gravity and then on all that sophisticated stuff. So he did this program sometime in 1984. And then he tried to quantize the three-dimensional metric, okay, and he was able to do it. Okay. So, so the idea is instead of having just a Lie algebraic correspondence, he looks for a more global version of that correspondence, and that is what is called the canonical group. So what is a canonical group? Is any group transformation on the phase space that keeps your symplectic form invariant. Now, if you remember classical mechanics, your equation of motion, for example, for F, for example, F dot is related to the Poisson bracket. Oh, sorry, X dot is related to the Poisson bracket, X and H, okay, the Poisson bracket X and H, and P dot is related to the Poisson bracket of P and H. H is your Hamilton. So in other words, if you keep the Poisson bracket invariant, you keep your equation of motion invariant. Okay, so in other words, over here you have a scheme that tells you, okay, you have to find something which is actually telling you how to pick out the observables, and that is essentially the thing that's mentioned here. So you can read the rest if you want to. So once you have that, so you get a canonical group. Once you have a canonical group, then you find the unitary representation of that group, and that provides the quantization method. Okay? That gives you the operators, because unitary operators essentially is EI something, okay, and that something will be the giving you the Hermitian operators that you need for quantum mechanics. Now, the other thing about that is that the theory of group representation, we know that you can have different what you call inequivalent unitary representation. Okay, so when you have that, once you have that, that will tell you, okay, given a particular symmetry, you are able to get different quantization, and they are inequivalent. And this equivalent representations tells you a kind of, okay, there are things which are having different properties. Okay, so let me try to give you an example. In this particular case, it's a bit difficult, but one of the things that I work on my PhD was to be able to show that, okay, this will give you certain representation that even, I work on the torus, for example, okay, you get representation for the torus, okay, wave functions on the torus, but you also get something else, which is not equivalent to the the case with the toruses. Okay, so you get you are able to exhaust the possibilities of building up quantum theories in this way. So okay, I think doing too much over here. Now let me just go to this point where what we are trying to do now is to extend this to compact phase space. Remember the cotangent bundle having at least one of the dimension goes to infinity, so it's not compact. Okay, so here we need to do this. If you remember, for example, okay, take the case of the harmonic oscillator. Why is it having a discrete spectra? Is because you always allow it to have the motion to be bounded. It's bounded within a certain interval, for example. And that gives you the discrete spectrum. So the angular momentum, for example, you know that that's going to be discrete because everything is simply limited to a particular, say, radius, for example. Okay? So what we want to do is to be able to extend canonical group quantization to this compact phase space. We are still trying to verify a few things, but one of the things that we know that, okay, for the case of angular momenta, we know that we need CP1, so you get a Bloch sphere instead, okay? And the Bloch sphere will actually tell you, okay, no, you need a rotation kind of thing, but now once you go to the quantum case, you need a complex version of rotation, which is your unitary groups. Okay? So, and the unitary groups will be now the canonical groups that acts on the complex projective space. What is complex projective space? They are just a set of lines, okay, in the n-dimensional, say you imagine the Bloch sphere, okay? So imagine the lines passing through the origin, through the sphere, and then the points on the sphere will give you all the different quantum states. If you have done the Bloch sphere before. Okay? So we are trying to do that. But the problem here is we don't have a cotangent bundle structure, and the idea of polarization is not really there naturally. Okay? But there is a natural, well, there is an intrinsic polarization because you have, when you write down the coordinates of CPN, you have Z and Z bar. And your symplectic CPN is the complex projective space in general. There is already this, your Z and Z bar acts like your X and P. So what we wanted to do to this is to treat this like your classical phase space, and then hopefully we get all the representation of angular momentum. So that was the hope. So part of it is being done by my PhD student, Azazi. Okay. John Bias was also working on something similar, but we have not seen anything published by him as yet. Okay, so the other, oops, I've forgotten to put this as superscript. The other thing about CPN is that we wanted to do something else called symplectic topology, which is a new area of maths. I think it began in 1985. It's not really known to the physicists as yet. Okay, but let me just mention what it is. This non-squeezing theorem is just almost looks like Heisenberg uncertainty principle. Okay. It says that the phase space, you cannot squeeze it too thin, okay, in one direction or too thin in the other direction. So there will be always an area. And that area is essentially just like your area, like your X and P. You are limited to see how much accuracy that you have for X and accuracy you have for P, the Heisenberg uncertainty. So it is something that we thought that, okay, this must have a role in formulating this Heisenberg uncertainty principle. You have a non-exclusion theorem in the classical case, and then in the quantum case, it will actually give you the uncertainty. So the only person that I know that's working on this is Maurice de Gauson, so a mathematician essentially. So we wanted to do something similar, but now we want to do it on CPN, and we have not been successful for that. So so there is always success story and failure. So yeah, okay. The last one is probably again, I wanted to say a lot more, but it's just I didn't have time to prepare too much. So the last one is something which I call how should I say? You have the idea of geometry, so it tells you, okay, what's the relevance of geometry? The relevance of geometry is the fact that you know that coordinates that you put on spaces are artificial. Like you see this three-dimensional space that we are in at the moment, you don't see your coordinates. You don't see coordinate axes, but we know that the space is there. Okay, so geometry allows us to formulate things without necessarily depending on the coordinates. So that's the beauty of having a geometric version of a theory. So as I said earlier on during the history part, okay, von Neumann was the one who sort of solidifies the mathematics for quantum mechanics. Okay. And one of the things that he does in that particular thing, that book on mathematical foundations of quantum theory, he uses a lot of how to build up the Hilbert spaces and things like that. But later on, after he wrote that book, he wrote a letter. Can't remember to whom, forgotten the persons. He wrote a letter to his friend, I think, Birkhoff. Okay? I would like to make confession which may seem immoral. After formulating quantum mechanics on Hilbert spaces, he says, I do not believe absolutely in Hilbert space anymore. So after he's constructing the maths for quantum theory, quantum mechanics, he says, okay, I'm giving up that particular formalism. That particular, what he's trying to do next was to look into geometry behind quantum logic. I will not be able to say too much over here, but quantum logic is just you look at propositions that are able to be satisfied by quantum mechanics, and this uses what we call the projective geometry. And the CPN that we had earlier was essentially a complex projective geometry. Okay. So von Neumann was working on this, but not successful. I mean, there are a nice book to read was by Varadarajan, Geometry of Quantum Theory, and talks about making propositions from projective geometry. But much later on, there is these two guys. Essentially, one of them is Bob Cooker, and the other one is a computer scientist. And Abramsky is interested in logic, and of course, within the computer science department. Cooker was doing work in quantum logic before that. Okay. So what they found, there are certain theory in maths called category theory. So category theory is sort of generalized similar features that you find in certain certain field of mathematics. So you collect all these similar features and try to understand it in the form of category theory. So it's too complicated for me to say here. But they are able to work on those, and category theory essentially, the way I see is like maps. Okay? It's just like your quantization map previously. So here you just talk about maps between one space to another space. So and then you are able to compose it. So that becomes a new way of understanding quantum mechanics. It's called categorical quantum mechanics. And they have reproduced all the known quantum mechanical results, at least for the finite dimensional ones, through this use of category theory. And the other thing that within the school of pure mathematics and theoretical computer scientists, they know that there are certain types of categories called the monoid categories can always be translated into graphical language. So if you write an equation over here which is involving mappings, okay, you can translate that to diagrams. Okay? So diagrams becomes a bit more graphical. And you can always convert an equation over here in terms of mappings to an equation over here in terms of diagrams. So Cooker and he has a huge number of students before this, started to produce a graphical calculus called the ZX calculus. And ZX calculus at this stage has been quite popular because it helps to formulate the processes that you need to manipulate qubits, or more generally qubits. Okay? And they have actually essentially used this to simplify quantum circuits. So initially I wanted to introduce a little bit, but I don't have time, I think. So so they have done this. There's a lot of work being done here. We have not done anything original so far on this part. I have a master's student working on this. So we wanted to see something else. Okay. Our idea was to explore the quantum foundation stuff with some geometrical ideas using the projective geometry. So we have not come to any original ideas as yet. But these are the things, some of the trends that you can actually look at if you want to. The maths is a bit daunting, complicated, but Bob Cooker sort of told me that you can start teaching high school students using the graphical language. So he's producing a book sometime in December, which is aimed at high schools. So and he's doing some experiments at the moment. He teaches, somebody teaches quantum mechanics in the normal way in the universities. And then he'll be teaching, he and his collaborators will be teaching high school students using this graphical language. And then they will be given some exams to actually get some results and see, compare who gets the result first, or something like that. And that is probably one of the, I think, neatest thing that I thought. You can think of this like if you try to do quantum field theory, you do all the loop calculations, but you can get simply by writing the loop calculations in terms of Feynman diagrams, something like that. So I think that's probably all that I can say. This is Bob Cooker. He's a rocker. This is in a conference that I organized sometime in a few years back. And this is another guy. I wish I didn't get the chance to say some work of his, which is related to symplectic geometry, the idea of non-squeezing theorem and things like that. He has this paper called the epistemic nature of quantum states. And he was able to show, using a toy model, he was able to show that using the toy model, he can actually reproduce most of the properties of quantum mechanics. And the idea over there is to be able to limit your, what can you say in terms of information. And I believe there is an Indonesian working in this area as well, but not in terms of the toy model or the categorical quantum mechanics, but it's using the idea of limited epistemic or epistemic restrictions. I think he produced a few papers. Probably you know the person is Agung Budiono. So I think that's probably all that I wanted to say for today. Sorry if it's not enough. So I'm open for questions. Thank you. The last slide.
Okay, thank you, Professor Hisam, for the explanation. Now we are going to have the question and answer session. For those who want to ask, you may ask directly by using the raise hand feature in this chat, or you may write what you are going to ask in the chat feature.
Okay. So have a look at the chat.
Okay, there is one question from Fitriana. Oh, okay. We have one person who raised his hand, Mr. Albert Sulaiman. Perhaps you can unmute your mic, Mr. Albert. Can you
Hello?
hear me? Yes.
Hello, yes. Okay.
Yes.
Thank you very much. Very nice presentation, Professor. But I have some question. But the first is, I think it's very interesting if we take it into account about the nonlinearity in quantum mechanics, because in classical physics, nonlinearity give the new perspective of our nature. And my question is, isn't there any problem with wave function interpretation or Heisenberg's principle if we take it into account the nonlinearity? And the second is, how about to quantization? Maybe instead of canonical quantization, it is possible if we use Feynman path integral. I think this is more straightforward, or yeah, I don't know exactly. And the third, instead we do the fundamental problem, it is worth if we do some research in more application. For example, if we have known problem in quantum mechanics and we recalculation by taking into account the, for example, nonlinearity, and we show the effect of nonlinearity in the ordinary quantum mechanics problem. It is worth reset, bad reset, or good. How about your opinion, Professor? Thank you very much.
I'll try to answer what I can remember. First, about the nonlinear spaces. I think there should not be a problem. Okay, there should not be a problem. Of course, no. Generally, the nonlinear spaces can be described by some geometry. Okay, and we already have a sort of more or less general, but prescription for producing quantum theory on those spaces. But one has to be very careful to say you can do everything with this kind of prescription. When you talk about spaces, there are spaces that are even ill-behaved, okay? Things where you have singularities. So I think at the moment, as far as I know, there are only certain types of singularities that can be that can be treated in this way. And I think probably, okay, that's one aspect. The other aspect that people already quite, they have actually investigated nonlinear system using quantum mechanics. We talk about quantum chaos. Okay? So, but people still do not really quite understand the nonlinear feature, how the nonlinear feature in the classical case correspond to the nonlinear feature in the quantum case. In a way, they do feel that the quantum features sort of stabilize the chaos kind of thing. Okay, so these are things unknown to people working in quantum chaos. But no, I think it's still poorly understood. I think there are a lot of I'm aware, for example, people are working on the early 90s, I suppose, in quantum chaos, but I'm not sure what they have done at this current stage. The other thing was you were asking whether there was one other question which I forgot. The other thing was whether it's worth to. It's difficult to tell because unless you're working on the application itself. Okay? I know for some certain things you already have applications in treating certain nonlinearities, for example. Okay? But to find a nonlinear system within the context of say microscopic version of that. So that is actually much more difficult in some sense because there are not many microscopic nonlinear versions that we know how to handle, put it that way. So, but it is an important thing because one of the things that people try to do, for example, this is coming from the work in sometime in the 90s, for example. People know that, okay, we have microscopic device like wires attaching to a device in that way. So you get the wires can be treated as singularities. Okay. So, and some singularities can be modeled by some hyperbolic spaces. I've worked on some hyperbolic spaces before, and people look at, okay, one of the nicest thing about trying to understand quantum mechanics on hyperbolic spaces is that you have both the continuous spectra as well as this discrete spectra. And what makes it difficult is to understand where the discrete spectra is, because it's embedded inside the continuous spectra. So some of the works that we did was to actually try to get spectra of this version. Okay. And hopefully, it can, that is a toy model for certain devices in the microscopic scale. Okay. So you can talk about those.
Thank you very much, Professor. Thank you.
I've forgotten what the other question is. Sorry about that.
Okay, thank you, Mr. Albert, for the question and Professor Hisam for the explanation. Next, we have question from Ms. Fitriana. Okay, this is what she asks about. I'm sorry if my question is out of topic. I have searched some of your publication related to my research area, material science. I am interested in researching density functional theory, but we still need help with how to start. I saw some of your publication about DFT. Please give some suggestion on starting research in the DFT field.
Okay, I'm not the expert inside density functional. These are mostly done by my colleagues or probably my students I co-supervise with other supervisors. But let me just say that I'll say what I know, okay? That's easier because density functional is essentially a model. Okay? So you're trying to model, one of the problems in the way we do physics is that we try to do a closed kind of system. You look at one particle, how they interact with another particle that we can actually do. You put more particles in, then we start not knowing how to do things. Okay, so instead of having consider all these few other particles, you consider particles interacting with a potential. So this is essentially the job of the density functional theory. In my case, my interest in density functional theory is looking at those. I've forgotten what the name of it. So you look at what kind of information that you can extract. Okay. So, for example, you have a Hamiltonian that tells you how the particles interact. Then you do some kind of local tracing, partial tracing, and then you get what we call the in terms of quantum mechanics, because I always look this in terms of density matrices. For example, we look at reduced density matrix. Okay. So, and this reduced density matrix can be of many forms. So the one that's being used in quantum information are usually the one body reduced density matrix. So in other words, like the EPR problem. So you want to know, what information that you can get locally from each party, A and B, for example. Okay, so you sort of partial trace these variables that are associated with subsystem A to get information of subsystem B. The general case is still unknown. For example, the two-body correlation function. How you actually how do you do how do you understand those? I think that is probably my kind of problem rather than trying to DFT is already pretty much well developed because they have softwares now. So most of the time people actually use the software to work out the density functional for each material. Okay. So I'm not sure how to answer them. Is that enough? Because I'm not the expert for that part of the field. It's my colleagues who are actually doing it. My ex-PhD students are now doing DFT.
Okay, Ms. Fitriana, perhaps you can type in the chat feature. Okay, she said enough, Professor. Thank you. Okay, perhaps we can move on to the next questions. Okay, this question from Mr. Eko Prihandona. Assalamualaikum, Professor Mudin. My name is Eko Prihandona from Muhammadiyah Metro University. I want to ask about how can we distinguish an equation for an electron, for example, as a particle and as a wave. Because as far as I know, electron has particle duality properties, a wave properties in an atom, and a particle properties on instant photoelectric effect. And how can we interpret Bell's inequality phenomena in our everyday life? Thank you. Best regards.
Okay, this is something that I've forgotten to bring it up. One of the reasons why I prefer remember I mentioned there are two different options, the deformation thing and also the geometric quantization. Because the geometric quantization insists on having this sort of partial dependence of the phase space. Okay. So what do you get? You always try to find functions that obeys eigenfunctions, for example, of the derivative. Now you know what the eigenfunction of a single derivative. Okay, the eigenfunction of a single derivative is just your exponential. So if you put a complex number to it, then you have waves, essentially, plane waves, exponential ikx. So that's why for quantum mechanics, you have this duality coming from the wave equation of Schrödinger. You have this possibility of describing things through the eigenfunctions of the momentum operator. So how do we know when we are describing particles of waves? Actually, we don't really, I mean, put it this way, we always treat, okay, we are writing down an equation for a particle in terms of wave functions. We always do that. So in other words, we treat both particles and waves at the same time. But when it sort of being localized, meaning you do the measurement, it sort of goes into a direct delta function kind of thing. It gets localized. So this is what actually happened. And people still do not understand that. This is essentially the measurement problem or the wave function collapse kind of problem. So it's not really properly understood, even to the experts. But we do understand that when we write equations for particles, we are also writing wave equations for them. And I think I should also mention another thing. Normally we talk about wave functions as functions on position space. Today, when probably some of you might know this, people are talking about topological materials. Okay. Now they are looking at functions. There one investigate the momentum space more than the position space. And people are looking into those kinds of momentum space functions to understand those topological materials. So I think if you have a good basic understanding of what's going on in quantum mechanics, you should be able to understand those kind of things.
Okay, thank you, Professor. Perhaps another question. Okay, this is from Mr. Utama Alandeta. What is the physical meaning of the star product in the deformation quantization? And the second question is, what is actually the definition of quantization in this topic?
Okay.
Okay.
Put the question back on.
Okay. Okay. Yes, this is the question, Professor.
Physical meaning. Okay.
Yes, the physical meaning of the star product in the deformation quantization. Perhaps the
This
co-host.
is really why deformation quantization are more suited for mathematicians, because there is no, as far as I know, there is no real physical understanding of what's going on in the star product. So the star product normally discussed within the mathematics community more than the physics community. And the other thing about it is the star product treats it just like a particle in a way, but no, the functions of the particle are having this strange product between the properties. Okay, so these are things that makes a little bit odd in some sense, but it does give you answers that you need in terms of quantum theory. What is actually the definition of quantization in this topic? You mean the deformation?
Yes, Prof.
Well, can I share back my slide just now? Let me just share. Go back. Oh, I didn't have it. Okay. Now, if you remember in the ordinary commutator that you get in quantum mechanics, it's just F times G minus G times F, right? So that gives you the commutator. Okay. So here is an analog of that commutator. So by imposing this star product, you are able to make correspond to the Poisson bracket. But remember here, it's not operators. Your F and G over here are not operators. They are just functions. So this is why I said they are not giving you the Hilbert space. Okay, you are just dealing with functions, but those functions obey certain product rule, which is certain kind of multiplication, which seems very strange. So that is essentially the difference between the two types of resolution of that I mentioned earlier. So here, F and G are just simply functions. They are not operators at all. But yet you get that feature, okay, this part is just like your commutator and this part will be the classical. Okay? So there is a correspondence between the commutator over here with the Poisson bracket. So that is the idea of quantization. But if you want to go into, okay, how do you get, say, Hilbert space? They don't care. If they want to build a Hilbert space, it will be an extra step. I want to unshare this.
Okay, thank you, Prof. So is it possible if there are no Hilbert space, but we have some function about that?
Sorry, I can't quite get.
Is it possible, you say that maybe there are no Hilbert space?
Yeah.
Is it possible to have the function, that kind of function, and
Functions are just like that.
Yeah.
Sorry.
Sorry.
Okay, the functions that I mentioned over here is functions on the phase space. They are not wave functions. So when you talk about Hilbert space, you are talking about wave functions.
So the function is just a function, not wave function.
They are not wave functions. They are just like functions for a particle.
Okay, thank you, Prof.
You can ask me other things if I can answer. Sorry. No, I meant wanted to say a lot more, but didn't have time to prepare. What is quantum entanglement? Okay, that's a good question. How should I start? Okay, entanglement, normally one would have at least two parties to be able to say. So in quantum theory, normally people don't think too much about this. No, normally in quantum theory, when you have two systems, subsystem A and subsystem B, for example, you can say, okay, I'm going to quantize subsystem A, and then the other person say, I'm going to quantize subsystem B. But how do you actually make the combination between the two? So then people say, okay, you do a tensor product. So you have a wave function and in subsystem A and a wave function in subsystem B, tensor product. Okay, so that if you can actually just do that, then this is not an entangled state. The one that's being entangled when you do the tensor product is you are able to do superposition as well. So when you do superposition, onto the product, the tensor product, then you probably have the idea of entanglement. Example, for, in this particular case, an entangled system of A and B, there will be perfect correlation between there will be some strong correlation. If you have a spin zero system, for example, one spin up, one spin down, okay, and then you separate them, and then you only do operations on one of them, what you call locally, then if we detect this to be spin up, remember this, the total spin are zero, then we know that the spin is going to be spin zero. Okay? So there you have this perfect correlation thing. You know one information on this part of the system, then you also know the information on the other part of the system, even though if the systems are actually far away. The one that's a bit, that itself, it's difficult to actually do experiments to show what is unique in terms. You can also think of classical system having that thing. If I put two shoes, one is the left part and the other is the right part, you know that, okay, if I separate the two shoes together away, then I always have that, no, this is going to be left, this is going to be right, or this is going to be right, or this is going to be left. Okay, but there you, in the classical case, you don't have the superposition state. Here in the superposition state, you don't really know which is this left or right, or this left or right. But you still have that strong correlation between the two. I hope that gives you some idea about entanglement. And entanglement is actually, to me, it has been a lot been discussed in the popular literature, but it tends to sort of mystify them. But in reality, you know there are correlations that exist in many particle systems in condensed matter. So by right, those that you find, you don't really actually see those kind of correlations, okay, in classical, but you actually see them in materials. They are quantum correlations essentially. And by right, you should be able to rephrase things in terms of entanglement. So there are a group of school of people who are actually trying to rephrase what they find in condensed matter in terms of entanglement.
Sorry, Prof, I have a follow-up question about that.
Okay.
So is that intrinsic quantities like Einstein said, or the information travels spontaneously or exceed the speed limit of the light speed?
Okay. I wanted.
Or it is still debatable.
Okay. Actually, I wanted to say much more, as I said, but I didn't have time to prepare. There is another property which is also a quantum mystery. Okay, it's the fact that you cannot really assign values before measurement. Okay, and this is actually known to most quantum physicists. Okay, meaning if you don't measure, you don't know what the values are. So in other words, if I'm not making a measurement, then I can't say anything about that thing. So this is like saying that, is the moon there? There's a Mermin is, I think, the person. Is the moon there if you are not watching the moon? That kind of thing. Or something like, or if the tree falls down in the forest, does it make a sound? Kind of thing. It may seem a bit ridiculous when we talk about macroscopic objects, but in quantum, at the level of microscopic, they do behave like that. meaning you cannot see that they have certain properties until you make a measurement of those properties. So, it's a strange kind of theory of quantum mechanics. Okay.
Thank you, bro. It's still mysterious, yeah.
Actually, there is not. If you remember Speckens, the guy that was beside, he has a way of understanding this. Because what happens is when you do measurements, there might be something. The underlying reality has certain states in it. When you do measurements on top of it, you're sort of making a projection. For example, like this kind of thing. So you start to see only part of your hand, kind of thing, the one that interacts of this hand with the other hand. And that is the information that we get from measurement. The true nature of the other hand is still unknown. And this is essentially the toy model that you did. It's a nice paper if you want to read it. I think it's epistemic nature of quantum theory.
Okay. Thank you, Professor Hisam, for the explanation. So we don't have any more questions because that's the last one from Mr. Utama Alan. And before we close our event today, we would like to take a photo session. Perhaps the audience here can turn on their camera because we are going to have the photo session. Bapak Ibu mungkin bisa dinyalakan kameranya sebentar karena kita ada sesi foto bersama. Okay. Mr. Alan, can you help me to screenshot to okay.
Sampun, Bu, ya sudah.
Okay. The first slide. Okay. You ready? Okay. Okay, perhaps the next slide, second slide. Okay, thank you very much, ladies and gentlemen. Okay, thank you so much, Professor Hisamuddin Zainuddin, for the explanation today. It was very interesting information for us about the quantum. And Bapak Ibu sekalian, thank you for joining us in this occasion. We hope that we will meet again in the next session, in the next occasion with JPFA workshop. And thank you for all. Wassalamualaikum warahmatullahi wabarakatuh. Thank you, Professor.
Thank you, Bro.
Thank you. Bye, everyone.
Yeah, thank you.
Assalamualaikum.
Waalaikumsalam.
Waalaikumsalam.